All right, so if you're on Zoom, please type something into the chat to let me know that you are here. Today we are going to be talking about power factor correction. But we might work an example problem or two before then. Several prepared. Okay. That one's a whole bunch of work that I don't want to do. It's too similar to circuit one. All right, so before we move into power factor correction, let's look at a, in my opinion, fairly straightforward example problem. So we have a system that looks something like this. We have an RMS phasor voltage source. To which we have connected a transmission line network that has a characteristic impedance of 0.1 plus J 0.2 ohms. And that transmission line network is used to feed a series of loads. 0.1 and 0.2. For these loads, we do not actually know their impedance, but we have measured certain quantities about them. So load 1 here on the left, we know that it is absorbing 30 kilowatts of power at a power factor of 0.8 leading. Load number 2 is absorbing 20 kilovolt amperes of power at a power factor of 0.9 lagging. And over here we have load number 3, which is absorbing 10 kilowatts at a power factor of 0.8 lagging. And we have measured the voltage drop over our loads to be 480 angle of 0 degrees volts RMS. And our ultimate goal is to figure out what the source voltage is that is supplying this system. Okay. And while we're at it, we'll also figure out the power factor of our source. Okay. So, not entirely sure who taught some of you guys circuits 1, but did you go over how to determine the complex power absorbed by a load described in this way at all? You think so, or you don't think so? Okay, so several people are saying they don't know how. Okay, that's fair. All right. In industry, typically speaking, if we get an electric motor or something like that we're going to have to hook up to a system, we don't tell you that its impedance is this and that because it depends on the frequency and the speed at which it's rotating and all that kind of stuff. We would typically know how much average power that it's going to draw and the power factor at which it operates, and the voltage at which it is rated for. And that is literally all of the information that we need to know to be able to determine the entire complex power for the system, okay? So recall from class on Monday that the power factor is equal to the average power, P average, divided by the apparent power, S, and this is also equal to the cosine of our power factor angle, theta S, okay? These are relationships that we developed just 2 days ago. So using this, we could say that the complex power absorbed by load number 1 is going to be S1, which is the apparent power absorbed by load 1, with an angle of theta. Let me just do theta 1 instead of theta S1. Theta 1, okay? So I am starting off under the assumption that I can express my complex power as a polar form complex number, which I obviously should be able to do. So looking at our relationship for the power factor, which we know, for load number 1, we are told that we have 30 kilowatts being absorbed. Is that quantity average power, apparent power, reactive power? Yeah, so average, reactive, or apparent? Average. How do we know that it's average? Because it's in watts. Absolutely right. So we have the average power, okay? I want to get the apparent power, S. How would I do that based on the equation that I have? So if the power factor is the average power divided by the apparent power, I would argue that apparent power is then the average power divided by the power factor, right? So that would be the average power absorbed by our load divided by the power factor of our load. For our phase angle, how do we get the phase angle theta S based on what we have written here? Arc cosine, okay? So the arc cosine of the power factor. What is important about whether the power factor is leading or lagging? Anybody remember that from Monday? Right, so negative would correspond with leading or lagging power factors. Leading power factors, absolutely right. So just knowing the power factor and the average power, we are actually able to determine everything about the complex power of this particular load, right? So if we substitute in our numbers, that's going to be 30 kilowatts divided by 0.8 negative inverse cosine of 0.8. And so that gives us a complex power of 37.5 angle negative 36.870 degrees kilovolt amperes, right? So if we have kilowatts for average power, we need to have kVA for our apparent power. So let's look at load 2. Expressed as a polar form complex number, all right? Now let's look at the amount of information that we were given about it. We're told the power factor of 0.9, and it's lagging, which means that we know our angle should be positive. We are given that it is absorbing 20 kilovolt amperes. So what quantity do we have if we're told a number in kilovolt amperes? the apparent power, right? So if we already have the apparent power, do we need to divide by the power factor? No, okay? So this is going to be S2 with an angle of positive arc cosine of power factor 2, which is going to be 20 kVA inverse cosine of 0.9. Looks like 20 with an angle of 25.842 degrees kilovolt amperes. Okay. Finally, for load 3, we're going to have S3 angle 3. Because we are given average power, we were told it was 10 kilowatts, so we were definitely given average power. We'll divide that average power by the power factor. So that is going to be P3 over PF3 with an angle of the inverse cosine of PF3. And it's positive because we have a lagging power factor. So this is going to be 10 kilowatts divided by 0.8 inverse cosine of 0.8 looks like 12.5 angle 36.870 degrees kVA. All right. So now that we know how much complex power is absorbed by each of those 3 loads, we can bundle it all together and treat that as one large composite load that is simply absorbing the total amount of complex power, okay? So I'm going to say that S total is equal to S load 1 plus S load 2 plus S load 3. And when I add all 3 of those numbers together, I get 58.339 with an angle of negative 6.182 degrees. So while it's not part of the problem, what can I say about the composite load based on the sign of my phase angle here? It's going to have a leading power factor, okay? So does that mean it's capacitive, inductive, or resistive? Capacitive, right? Not purely capacitive, because it would have a phase angle of not negative 90 degrees if that were the case, but it is a capacitive load, right? So now that we know the total complex power absorbed by the load, and we know the voltage drop over the composite load, we can figure out how much current is flowing through our transmission lines, right? So I'm arguing that we have enough information to now determine this quantity, which I am going to call IW, and it's going to be an RMS phasor. I'm calling it IW because it's the current flowing through a wire, all right? Anybody have any ideas on how we might go about calculating that current? If it helps, I'll bring back our picture. Yeah, so if I know the complex power of the composite load and I know the voltage drop across the composite load, I should easily be able to determine the current flowing through the composite load, right? Or the total current flowing into the composite load, as it were. So using our complex power relationship, we know that S total is going to be equal to the voltage drop across our load, which I'm just denoting as VL, times the complex conjugate of the current flowing into the load, which I'm calling I wire. We can rearrange this guy, and we would find that I wire is equal to S total divided by my RMS phasor voltage VL conjugate. Okay. Everybody fully understand how I got from here to here, because it's rather important. Okay. So if I divided both sides of my left-hand equation by the RMS phasor voltage VL, what I would have is the complex conjugate of my current is equal to the complex power divided by my voltage, right? If I take the complex conjugate of the complex conjugate of my current, what do I get? The current, right? Because I'm changing the sign on the imaginary portion, and then I'm changing it right back. So if I do conjugate of conjugate, I get I wire, but I have to do the conjugate of the other side of the equal sign as well. Okay? So if I put numbers in here, this is going to look like 58.339 with an angle of positive 6.182 degrees kilovolt amperes divided by 480 angle 0 degrees volts RMS. Now I want to be very, very clear here. I'm taking the conjugate of this fraction, which means I have the conjugate of the numerator and the conjugate of the denominator. But because my denominator had a phase angle of 0, negative 0 is the exact same thing. So if I had started out with a phase angle of, say, positive 20 degrees, I would need to put negative 20 degrees here because I have to do the conjugate of both the numerator and the denominator. That is a very, very common mistake I see all the time, so I'm just warning you, don't do it. All right, so performing this math, I get a result of 121.540 with an angle of 6.182 degrees amps RMS, okay? So I now know the current flowing through my transmission line. So let's go revisit our original drawing. How can I use that information to determine my source voltage? Anybody have any thoughts? So I could find the voltage drop across my transmission line impedance. Okay, so I'm going to do that in orange. I'm going to call this voltage VW. Okay, and that's over that combination of the resistor and inductor in series. And then I could use Kirchhoff's voltage law and say that my source voltage is simply the voltage drop over my transmission line, V wire, plus the voltage drop over my loads, right? So I'm going to do just that. The Vs is equal to VW plus VL, where VW is just the current flowing through it. So that is I wire times the impedance of my wire. Do I need to conjugate this current? No, right? I'm calculating a voltage, not a power. So I don't need to take the conjugate of the current. Plus VL. So that is going to be 121.540 angle 6.182 degrees amps RMS times 0.1 plus J 0.2 ohms plus 480 angle 0 degrees volts RMS. And when I add all of those numbers together, I get 490.128 with an angle of 2.979 degrees volts RMS. So I have my source voltage and I have my I have my source voltage and I know the current that's leaving my source. So I should be able to determine the power factor at which my source is supplying power very easily, right? So because I'm trying to find the power factor at which my source supplies power, I just want to make sure that the current is leaving the positive terminal, not entering the positive terminal. If it was entering the positive terminal, I'd be calculating the amount of current absorbed by my source, right? I'm using the passive sign convention that you guys learned in circuits 1, okay? So my power factor source, and I'm just going to put here comma SUF to let you know very explicitly I'm calculating the supplied quantity, is going to be the cosine of theta Vs minus the cosine of theta IW, because IW represents the current that's leaving my source, right? So that would be the cosine of 2.979 degrees minus 6.182 degrees. Because I added this to the question at the last minute, I don't have a number for it, so let me just go ahead and calculate that real quick. 2.979 minus 6.182. My calculator is in degrees. So I got a power factor of 0.998. My answer is not complete. If I asked you this question on a homework set or a test, which I am absolutely doing, I am missing whether or not my power factor is leading or lagging, okay? Not telling me whether my power factor is leading or lagging is like telling me that I have a current of 3 amps, but giving me no indication whatsoever of what direction it's flowing, okay? I need to have both things. So based on these numbers, is my power factor leading or is it lagging? Why do you say that it's lagging? Is the quantity positive or negative?
It's negative, it's leading.
Okay, yeah, so because the 2.979 minus 6.182 is going to be a negative number, this guy has a leading power factor. Everybody okay with that? All right. So now let's get into power factor correction, since nobody's asking any questions or anything. All right, so large industrial customers like manufacturing plants often operate at a power factor of less than 1 due to the presence of numerous inductive loads like electric motors. To avoid being fined by their distribution utility, a known as power factor correction can be employed to raise their operating power factor to an acceptable level. So let's say that we have a power triangle for a general inductive load, where this is our real axis, this is our imaginary axis, and this is our complex power, and I'm going to call it S old because it represents the complex power absorbed by our load before power factor correction has been applied. Okay? We have then an angle here that I'm going to call theta old, made between our complex power and our real axis. So if I wanted to improve the power factor at which this load operates, would I need to make that angle larger or smaller? Smaller, okay? Because cosine of 0 is 1, so we want the angle to be as close as possible to 0. Right? Okay, so we need to make it smaller. Are we in agreement on that? Okay. There are 2 different ways to make it smaller, one of which is completely asinine, and the other of which is the correct way to do it. Let's talk about the completely asinine way to do it first, okay? So let's say that I kept my reactive power constant, right? So I can make a projection of this power onto the imaginary axis. So this would give me Q old, right? So let's say that I made, and I can also do a projection onto the real axis, and let's call this guy P old. I'm going to give myself a little bit more room here. Okay. If I keep Q old constant, but increase the amount of average power that my load consumes, so if I increased its resistance only, I would have something like this. I'm not trying to open up mail. Wish I could draw a straight line. So here is the new average power, and this angle, theta new, is smaller than theta old. So I have increased my power factor, okay? Let's talk about why this is utterly moronic. I have increased my power factor by increasing the amount of average power that I consume. So in essence, I am running up my electric bill in order to avoid paying a fine, okay? Because average power is what we as a consumer pay for. So if we arbitrarily just increase the resistance of this system, we are literally avoiding a fine by paying a higher bill, which means we're not avoiding the fine at all. That is why this is utterly moronic, okay? Mathematically, it works. It is literally never done in practice because it costs everyone money. It is the worst case scenario, all right? Now let's consider a second situation. We have our imaginary power axis. We have our real axis. We have that same complex power, S old, whose projection onto the imaginary axis is Q old, and whose projection onto the real axis is P old. The other means by which we can increase our power factor or make this angle theta old smaller is by keeping the average power constant and reducing the amount of reactive power that our load is absorbing, right? So if I had a situation like this, to where we have some Q nu, we could see theta nu that our angle got smaller. We are not increasing our average power consumed, which means we are not increasing our electricity bill, and our power factor has increased. So the question then becomes, what do we do to our system, our original system, to make this happen? Well, we have some original amount of reactive power being absorbed, and we want a new amount of reactive power being absorbed that is less than our original quantity, which means obviously then that we have to be supplying some sort of reactive power to our system. We are going to accomplish that by placing a capacitor in parallel, okay? So if you recall from the equations that we developed at the end of class on Monday, the complex power absorbed by a capacitor, I'm going to call it S cap, was negative J omega C VRMS squared. So this is the amount of complex power absorbed. It's always going to be a negative quantity, which means the capacitor is supplying complex power. So graphically, what we are doing is we are adding S cap and S old together to get a new complex power, S nu. That's it, right? We're just adding vectors together, which is something you guys probably learned back in Physics 201, okay? So, just to be clear here, what we have is that S nu is equal to S old plus S cap. And then we can easily see that S cap is S nu minus S old. So this is the crux of power factor correction. All right. Really, our only other thing that we need to do is to figure out how to relate S cap to getting a specific value for C to achieve a particular power factor, right? Because to this point, we haven't actually brought the power factor into the situation at all. Okay. So if we look at this equation, S cap is equal to S nu minus S old. What we have is P old plus J Q nu. Okay. I'm saying it's P old plus J Q nu because the average power of our new complex power is still just P old, right? So that we are not changing our average power at all. Minus P old plus J Q old. And from this, we can see then that we have simply J Q new minus Q old, or J cap. Right? Where Q cap is the reactive power that is being absorbed by the capacitor. Okay. If we look at the equation that I have above here, right? So if we're looking at this guy where I have S cap is equal to negative J omega C V RMS squared, what is Q cap in terms of C and VRMS? So what's the relationship between S and Q? If you have notes, look at them.
It's the sine of S.
You're getting too deep in the weeds, okay? Don't worry about sines and cosines and this, that, or the other. S is equal to P plus JQ, right? So Q is the imaginary part of the complex power. Are we okay with that statement? All right. That's literally how we defined it on Monday, by the way. So what is the imaginary part of this complex number? It's everything but the J, right? Because J is the imaginary operator that's turning that thing into that. So we could say that Q cap is negative, sorry, I wrote down the J and it shouldn't be there. Negative J omega C V RMS squared. All right. So I know now I have two different expressions for Q cap effectively. And so what I can do is I can equate those two things and solve for C. All right. And so by doing so, what I get is C is equal to negative Q cap, where I just want to be very clear here, Q cap is always going to be a negative number, okay? Divided by omega times the RMS voltage drop across the capacitor squared. This is exactly equal to P old times the tangent of theta old minus the tangent of theta new divided by omega VRMS quantity squared. The reason why I've written it out this way, which is probably something you almost certainly didn't learn in circuits 1, is because this lets me put in my power factor angles directly. So this is directly relating it to the power factor, okay? So let's say that we have the following system. Sorry, 400. I couldn't read my own writing. Angle 0 degrees, volts RMS, operating at a frequency of 50 hertz. So this is our voltage source, and we are supplying that to a motor. That is absorbing 1 kilowatt at a power factor of 0.8 lagging. What we want to know is what capacitor value C will increase the power factor at which the motor absorbs from 0.8 lagging to 0.975. Okay. So, based on the information that we are told in our problem statement, how do you guys feel that we should approach this? What do we know? Do we know P old? Yes, it's 1 kilowatt. Do we know omega? What is it? I'm asking you specifically because you came into my office with a mistake regarding this earlier.
It's not 50 hertz.
It's not 50 hertz.
Is it times 3 pi?
Yes, time. So it will be 100 pi radians per second. Okay. This is a linear frequency f. To get omega, we multiply it by a factor of 2 pi. So we have, just to be clear here, P old is equal to 1 kilowatt. Omega is equal to 2 pi times 50 hertz is equal to 100 pi radians per second. What is the RMS voltage applied to the capacitor? Note, I do not want the RMS phasor. I only want its magnitude, okay? Yeah, 400, okay? So this quantity right here, VRMS squared, is the magnitude of the voltage squared, not the phasor voltage, okay? So that would be 400 volts RMS, okay. Do I know theta old? I don't know it, but we can find it really easily, right? So theta old would be what? Absolutely right. All right. And because it's lagging, it should be a positive value. So this is going to be 36.870 degrees. What is theta nu? Just the arc cosine of 0.975, right? Which happens to be 12.836 degrees. So now we have all of the different parts that we need to plug into this equation up here, right? So we can do that fairly trivially and find that the capacitor value is C is equal to 10.387 microfarads. So as part of your summer internships, depending on where you go to work and all that kind of stuff, you might be asked questions like this. Would any 10 microfarad capacitor work? Like if I went to the storeroom here in Nefkin Hall and just grabbed something out of the 10 microfarad capacitor bin, would I be okay? Who knows? So the reason why I'm bringing this to your attention, capacitors are rated for specific DC voltages and RMS voltages. It might say VAC, but when it says VAC on it or on the data sheet, what it means very explicitly is the RMS value of the AC voltage. So in order to correctly correct this power factor, we would need to have a capacitor whose voltage rating was at least 400 volts RMS in order to do this safely. If not, when we hooked up our power factor correction capacitor, it would literally explode. Too much energy is getting dumped in, it can't handle it, it blows up. So just keep in mind, practically, we also have to think about things like safety ratings and all that kind of stuff in order to do this properly. Okay, so we can do the calculation very trivially, but we need to bring it into the real world. We also need to think about the ratings of our different components and all that kind of good stuff. All right. So if it's in hertz, it is the linear frequency. Radians per seconds, it is omega. Angular frequency. Because it represents the speed by which the angle changes. So have you guys had Physics 202 yet at all, maybe? No, okay. Some of you have, some of you have not. Okay, so how would you make a capacitor withstand a higher voltage? Most capacitors are a variation of a parallel plate capacitor. Okay, this is a brief extra physics lecture, which is outside of the scope of this class, but we've got some time, so I'll talk about it. All right, so a parallel plate capacitor literally looks like a sandwich. Okay, we have a top plate that has an electrode on it, and then down here we have a bottom plate. I can't draw for crap. All right, and it's got an electrode. In between these two plates is what's called the dielectric. Okay? The dielectric could be vacuum or it could be air, and they are going to have different permittivities. Okay, so the material in between the plates has a permittivity that is based on the permittivity of a vacuum. Epsilon naught is the permittivity of a vacuum or the permittivity of free space, and it has a value of 8.854 times 10 to the minus 12 farads per meter. Other materials have relative permittivities that range anywhere from 1, which would be air. Air is really like 1.001 or something like that. It's really, really close to a vacuum. And then they could range up to 1,000 or so, depending on if you have a highly insulating ceramic crystal or something like that. So that dielectric material that is between the plates, I'm going to fill it in kind of pink kind of here. So we just have the filling of the sandwich has a specific breakdown voltage. What that means is it has a maximum value of voltage that can be applied before it effectively disintegrates and allows current to pass through it easily. So we make capacitors rated for higher voltages by putting stronger dielectric materials in between. Okay. How many of you guys, well, there's only a few ladies in here, but how many of you guys have ever unplugged something from an outlet and seen sparks or arcing or anything like that? That is the back EMF in the system, or the inductance of the system, actually causing dielectric breakdown of the air between the electrodes inside the outlet and the device which was drawing power. So you're actually, because of the abrupt change in current, you're actually causing voltages on the excess of 10,000 volts or more, which is enough to ionize the air and create an electric signal that jumps across from your outlet receptacle to the plug of your device. So that is dielectric breakdown, which is exactly what we would have happen here inside of a capacitor as well. I guess technically that should be there. Yeah, so. Yeah, so the price of a capacitor is usually dependent on its size. So let me explain what I mean by size here. So like if we went from a 1 microfarad capacitor to a 10 microfarad capacitor, it would typically be more expensive because the 10 microfarad capacitor needs to be 10 times larger. Okay, if we looked at the capacitance of this parallel plate capacitor, it is epsilon naught epsilon r A divided by D, where D is the distance between the plates and A is the area of the plates, right? So to get an increase in capacitance tenfold with everything else being constant, we need to make it 10 times larger. So that means larger capacitors are usually more expensive. And then as you need stronger and stronger dielectric materials to be able to handle higher and higher voltages, that also causes it to get more expensive. So while you might be able to pop on to DigiKey or something like that and get a capacitor for the experiments that we're doing in, say, 229 or 339 or something like that for maybe 20 cents, if you wanted to actually implement a capacitor for power factor correction at a large scale factory, you're talking thousands of dollars minimum. And it's going to be huge. It's going to look like there's a refrigerator attached to something. It's going to be that damn big.
I was going to ask for, like, we did a singular 1 kilowatt motor, whereas General Electric would have 1,000 conveyor belts.
Yeah. So like a 1 kilowatt motor is about 4/3 of a horsepower or thereabouts. A horsepower is 746 watts. So a 1 kilowatt motor is about 1 1/3 horsepower, which is a pretty small motor. If you have a whole bunch of them together, then yeah, it starts to look like something different. But I mean, if you were moving something large around where you needed to have a much larger motor, then you also run into issues of needing very large capacitors, these things as well. Yeah, so you would definitely want some sort of redundancy and all that kind of stuff in order to alleviate that. But I mean, there's going to be some places where you literally just need the torque of a large motor like that to be able to do anything, right? The bigger the motor is, or the more power it can supply, the more torque it has, which means it can move stuff better or more efficiently. So like if you wanted to build an electric car, like Tesla does and all that kind of stuff, they are not using 1 horsepower motors for each of their wheel assemblies, right? Because your car wouldn't be able to go very fast. We have 15 minutes left to class, but I do have another example problem, but I don't know that we can finish it in 15 minutes. So I might just post these notes online and we get out of here a couple of minutes early if that's okay by you. All right. We do not have class on Friday. Just want to reiterate that. So don't show up and be like, where are you? I'm in a meeting. So just to be very, very clear. I'm in a meeting and then I'm have to take like 7 people out the way. So we will reconvene on Monday where we will kick off 3-phase power. So before we officially adjourn, any last questions regarding power factor correction or anything? Yes, sir.
Do you hook up a multimeter onto like the complex loads, like the just like figure out what your resistance for its value is? Do that, or do you have to do that?
So for a motor, the impedance value is going to change depending on the speed at which it's operating and all that kind of good stuff. So you could, if you were to hook a multimeter up or something like that, right? So a multimeter, if you're measuring resistance, requires you to have your thing disconnected from the system, right? So if you measure the resistance drop across, if you measure the resistance of a resistor while it's in an active circuit, you do not get an accurate representation of its resistance. Impedance would be even more difficult, okay? So while your multimeter does have a setting to be able to measure RMS voltages, that really doesn't help you because that's only a small part of what you need to measure power factor and all that kind of stuff, right? You would need a multimeter to measure the RMS voltage. You would need a Hall effect sensor to measure the RMS current. You would need a way to figure out the phase angle difference between those two quantities. And then from that, you would know at which power factor it's operating and could then correct it.
You do that with the oscilloscope.
Yes, if you have the proper cabling and all that kind of stuff to measure current, because oscilloscopes are designed to measure voltages, so you need a specific probe to convert the current into a voltage signal that's matched to a specific resistor reference, usually 1 ohm, to make it a 1-to-1 relationship. And then you can absolutely figure all that stuff out off the oscilloscope, which is what you guys did if you did the experiment in circuits 1, which it sounds like you did. So anything else? Okay. Yeah, so you guys learned nothing. Cool. Well, you'll have fun in 229, finally doing experiments, I hope, by yourself. So we'll see. Okay. I mean, I'm saying that like that's not exactly what I did in the fall too. It got to a point where I was just like, it's going to be easier if I just do it, and it's safer because we couldn't have all the people around.
You said you didn't have the equipment.
Absolutely. So the Senior Design Expo is Friday. There's an invitational message or whatever from Dr. Hegab at 12:30 in the atrium. So I guess that's the large area when you walk into the ISB. The student presentations begin at 1 p.m. The electrical engineering presentations are in room 210, for which I am the moderator, and room 228, for which Dr. Batari is the moderator. By all means, come drop by and ask questions and all that kind of stuff, or just watch the presentations if you want to.